talk a little bit about a two-state system. So in this case, it will be a chain hanging from some support by some number n links. Okay, and there's a mass at the bottom, we'll call M. And these links have, they're not perfectly round, they're kind of shaped like an ellipse or something. So basically they're going to have one length that's longer than the other. So we can call the long length L. So from here to there, and the short length, let's call L minus A. So what we're going to try to figure out is the average length of this chain. All right, and it's going to be, we're going to say this chain is the difference in energy is on the order of the thermal energy, the temperature times the Boltzmann constant. So an example of like a real life chain where something like this can happen is, say you have a strand of DNA and it's all coiled up in a bunch of different configurations, and maybe you have a bead attached to the end that's being pulled. You can do this with some laser tweezers, and you want to know how far will the DNA stretch out. That's a little bit more of a complicated situation, but here in this analogy we've just got these links that can be either in the long orientation, or they can kind of flip sideways, like maybe like this one here, and this one. I have a few of them that look like they're more flipped sideways. So that will cause the chain to be shorter, and we have this mass which would be lifted against gravity. It does work, and so you have different energy states that are available to it. All right, so if there's a whole lot of energy given to the system, it'll have enough energy to maybe put more links into this horizontal position than what I've drawn here. But if gravity, is very strong, or if there's not thermal energy, you'll be able to pull the string out, or you'll be able to pull the chain out until all the links are in the long position. All right, so I'm going to go ahead and define I'll draw it down here a little bit. Here's going to be our E equals 0. So say all of these links were all stretched out completely. So that's what I'll define E equals 0 as. There are other, it might turn out prettier in the end if I picked a different E, but we'll just pick this one. Yeah, the answers will look a little rougher than what you might find. All right, so what we need to do is find out what the probabilities are for the links of the chain to be in the long, the vertical orientation or the horizontal orientation. And so if we just think of a bag of marbles or something, suppose I had a bag of marbles, and let's just say, I don't know, if we had some marbles with the number 10 written on them, and some marbles with the number 15 written on them, and I had a whole bag of these marbles, and I want to know if what's the average number if I were to take the average of the numbers on the marbles. What would I get? Something between 10 and 15. Well, the way we would do that, we'd have to know what their ratios are. So let's just say that there are twice as many of these 10 marbles as there are of the marbles with 15 written on them. So the way I would find, I'll just use the # hashtag, right, to say the average number that would be written on these marbles. Well, they'll be weighted differently because there's twice as many written with 10 written on them as there are of the 15. So there's going to be 2 times 10 plus 1 times 15. Can't really see that very well. That's a 15 in there. But then I have to normalize it. And so what I'm going to do is write down 2 plus 1 down here. So the 2 and the 1 are kind of weighting factors. They tell us how much weight to give each of these values. So in this case, what would I get? I'd get 35 over 3. All right, whatever that is. 11 something. Yeah, 11 2/3. All right, but these are weighting factors. Well, in this case, when we have an energy, each of our microstates will have an energy associated with it, and that's sort of like how each of these marbles has a number associated with it. If this analogy holds. So we need to know what are the different probabilities of these microstates. And what we know is that the weighting factors that we're going to be using are the Boltzmann factor. So we have the Boltzmann factor looks like this: E to the minus of the energy divided by the Boltzmann's constant times the temperature in Kelvin. So this is a weighting factor. It depends on the energy, and temperature will be the same for all of them. So really what matters is, going from looking at one microstate versus another is the energy. All right, so we need to know the energy of each microstate. And in addition to the Boltzmann factor, there's also multiple ways of getting the same macrostate, getting the same overall number of links in each orientation. So for example, one example of this is, these 2 links could still be in the shorter the horizontal orientation, but this link could be up here instead. And you just switch places with one up here. That's a different way of getting the same length of chain, but it's distinct from this one because even though there's still 3 links in the horizontal orientation, they're just in different places. And the way to take care of that is through the guess we have to define our, I'm going to use little n for the number of links in the horizontal. Alright, so I'll write that up here. N equals number of links horizontal. So the number of ways to get a microstate with this energy is just going to be the combination. So n, which is the total number of links. Pick or choose little n, which is the number of links that are in the horizontal orientation. So what this looks like is big N factorial divided by little n factorial, and then big N minus little n quantity factorial. Alright, so these are our weighting factors for our different states. Alright, so one thing we need to know is the normalization for the bottom here. And in this case, we call that the partition function. Usually we use the letter Z for that. Alright, so what this is like we just added up the weighting factors down here. So that's what we're going to do here. We'll take a sum over, so here's the combination part. And then here's and this is a sum over the energies. E to the minus the energy over kT. Like that. So this is our partition function. Alright, so now let's figure out E real quick. The energy. So we've called E 0 when all the links are in the vertical position. That means when little n is equal to 0, there are 0 links horizontal. And so when more and more of these links switch to the horizontal position, the mass is raised and the energy increases. So what we want to do is find so E. So E equals the number of links in the horizontal position, that's this little n, and now we want to know how much do they actually raise this mass for every one of these links that's in this orientation. Well, the difference between the two lengths is A. So the chain will get shorter by A for every link that is in the horizontal position. So n times A will be the total amount the chain shortens. And then we have G and M. So MGH, except in this case H is this NA. Alright, so now we'll write our partition function a little bit more fully. This is a sum where n, it could be 0, it could be completely stretched out, there are no links horizontal, or it could go all the way up to big N, where they're all horizontal. So this will be a sum from n equals 0 up to big N. So big N factorial, little n factorial, big N minus little n, quantity factorial, E. Okay, so now we're going to put in this E here, which is minus NAG big M divided by KT. Alright, so now we know our partition function, now we know how to normalize our probability. So now we need to just make a sum of what the values are multiplied by these weighting factors and then just divide by z here. So if we want to know the average length of this chain, we need the sum on top, and this again will be the same indices of the sum as we have in our partition function. Let's go ahead and write the partition function here on the bottom. That would be almost the same, except you see this is 2 plus 1 and this is 2 plus 1, except these ones are multiplied by the values that we're trying to get the average of. So these are almost the same. So I'm just copying z down to here. Big N factorial, little n factorial, big N minus little n factorial, e to the minus little n, ag, big M over kt. Alright, now we need to just know what the length is for, so again, let's go ahead and write the weighting factor first. Why not? That's the way it's written right here. So first we'll put the weighting factor, which is this whole factorial thing again. Alright, now the reason that we can't just divide this out is because there's the other term here. Now this would correspond to like this 10 and this 15 up in this example. But now we need to know what the length is of the chain for this energy right here. Alright, so we have n lengths short and n minus, so big N minus little n lengths long. So that, we'll just write that. So n short lengths, so little n times the short length, which is L minus A. And we're going to add that to the lengths that are in the vertical orientation. So that is big N minus little n, and then those lengths are L long, like this. And there we have it. So this will simplify down a little bit. I mean, because what is this? We have NL minus NA plus big N L minus little n L, so this will cancel with that. Alright, so write out this whole thing again. I'm just going to use some shortcuts a little bit. So I'm not going to write the indices. I'm just going to write in the combination. I'll use this notation: e to the minus NAG big M over KT. And here we just have big N L minus NA. Sum, the combination thing. And there we have it. This is the average length of that chain. Except I put an N instead of an M here. Okay. Any other mistakes? I don't know. But yeah, if you pick your zero energy, if you pick this in different places, you can get your answer into different forms. Something to usually pay what you want to look for are opportunities to use the hyperbolic trig functions. So anytime you see something like e to the something plus e to the minus something, all right, you can use like a hyperbolic cosine. Sometimes you'll have, you know, if this is a minus sign right here, you can use hyperbolic sine. If you get a ratio of them, you can use hyperbolic tangent, or cotangent, or something like that. So lots of times when you have an answer like this, if you were to pick an energy like halfway in between, so you get some, you know, to be your zero, so you get you would get two different energies, one that's positive and one that's negative. Sometimes you can get a positive and a negative, like in this little example, and make your answer nice and pretty with a hyperbolic tangent or something like that. But still, I think this form for the answer kind of illustrates what the